Hello everyone, welcome to my presentation. Today I discuss a conference paper from NeurIPS 2021. The paper title is DropGNN. The random dropout increase the expense of the graph neural network. This paper was right. The Paul Erdspap and his co-author, and this author from ET Zurich, Switzerland. I am Imrus Salehin. Today I present this research paper. So for the best presentation, I divided these papers into some content like highlights, introduction, problem statement, material and method, result, and conclusion. So first of all, we see the highlights. In this paper, DropGNN study, they execute the multiple run of the GNN on the input graph with some of the nodes randomly and independently drop in the each those runs. The main idea to execute not the part multiple different run on GNN, then they aggregate the result, these different runs into the final result. And the last of these, that they have analyzed the theoretical properties of DropGNN. So we see the introduction part. In graph neural network are the class of deep learning method designed to platform increase on data described by graphs. So the GNN are the neural network that can be directly applied to graph and provide an easy way to do node label, its label, and the graph label prediction task. So if we see this image, basically we all know that the neural network have archived incredible performance in the range of different applications. And one of the newest success story is that of the graph neural network on the GNNs, because some of the most interesting data out there is the structure as a graph, such as the molecular or the social network. So the third one is the problem statement. So the most GNN framework follow the so-called message passing method. This means that that is each round the nodes aggregate the embedding of their neighborhood, and the GNN can learn the different implementation of these aggregate or the update function. Also, because of these, whenever two graphs on two k-hop neighbors look identically from a node's perspective, and then the GNN will not be able to distinguish this case in any case on the face of the formally. And this message passing GNN can never have more expensive power than so-called WL test, which is the mathematical tools of the functionalized than the concept that two graphs look identically from a node's perspective. Then if we see the graph, the simplest example to see this is when we cycle of different lengths which can never be distinguished by the message passing GNN due to this. So let's look at these two graphs from the perspective of this node V and assume that all nodes being with the same identical function. Even we see the second graph. So this is the first round of V compute a value by aggregating the feature of the neighbors and combining this with its own. And also this is the new embedding of V now also depends on the two hub nodes of V, and although the final embedding that V compute is determined by trace respect of the neighborhood. And the same things happen in the large cycle. If we see the large cycle, so the same things happen in the large cycle. The V first compute the embedding based on the immediate neighbors, and the second round is uses the first round embedding of their neighbors, which depend on its two hub neighbors and so on. So the deterministic GNN will always compute the same final embedding to this graph, even though the graphs are different. And from the outside, we do some that info cycle. These two nodes of the representation actually the correspondent of two same node or the original graph, which is the sixth cycle of two nodes corresponding to the different or original node. So we see the final summary about the problem statement. So the GNN are the limited in their expressive of the Westphal lemma test and the heuristic to the graph isolation problem, and the GNN will always compute the same embedding. So for the advanced GNN, some limitation are also as follows, like the this often comes with the much higher time or space complexity for the stochastic metagraph. This is also the line of the work introduced the random node feature, which again has highly expensive power in the theory but often does not generalize to the new data. And so if we summarize the expensive of GNN implementation, so like this is the main expensive GNN implementation, like the run of GNN in the metagraph, extended GNN model and adding the random feature. So then we actually discuss about the material and method, how the GNN actually implement in this research. So first of all, we try to know about the GNN. Almost all the GNN architecture follow the message passing framework, and every node start with the embedding given the initial feature, or and one round of message passing has three steps. So in the first message step, node create a message based on their embedding and send this message to all neighbors. The second node aggregate all the messages they receive, and third, every node update its embedding based on the old embedding and the aggregate message. So usually the message, aggregate, update, and read out are the function with learnable parameter for interesting level layer of activation function. Then actually what is the drop GNN and what is the main idea of drop GNN in this research paper? So basically, drop GNN is the execute multiple independent run of GNN during the both, I mean the training and also the testing phase. And every node of GNN is removed with the probability of P and independently from all others node. If a node V is removed during the run, then the V not sent to receive any message to or from the neighbors and does not affect the remaining nodes in any way. So over the course of multiple runs, dropout allow us to not observe the d-hop neighborhoods around node U. But also several, I think the particular variants is the d-hop neighborhood, and in the different run the embedding compute or EU might be also slightly vary depending on which nodes are missing from the DHOP neighborhoods in the specific run. So actually the main approach of GNN with the dropout, so the multiple run of the GNN and is not. So if we see our method, if we see our graph, so in the first run we might be randomly remove the identical aids, and then we run the GNN on the graph. We can see in the graph in the first run. Then we see this is the second run. So in the second run, it might happen that we remove these two nodes and then run the ZNN on this graph. And what happened in the third node? So basically, the it may be the third node. There are no nodes are removed. So there are no nodes are removed. So we have the original graph and so on. So integrity, this method is allowed. So this is the third run. And so the integrity, this method allowed to not only observe the original graph but also different slightly the protected variants of the graph. And with this, we can often distinguish two graphs even when they look identical to standard GNN. So this is the main idea of DropGNNs. By running the GNN multiply times, slightly different variant of the graph, and we can learn much more about the structure. Of course, this is also means that after all the run, we will not have a single embedding for nodes, but instead we have the range of embedding. So we also need so-called run aggregation step in the end of the nodes, the learns of the combine these embedding and compute the ID different runs in the single final embedding. An important thing is you might recall the well-known regularization method. We also call this is dropout, but this drop GNN approach is very different from the concept because in their case they have a execute these multiple runs, so we can see the ISV, the run aggregate variables. So this is the method, and this is the result. So evaluate the technique of increased GNN expensive or challenging synthesis data set. So they basically highlight the best score of bold, and if we see here, they actually compute drop GNN, so GNN plus dropout. So the first column, if we see the dataset name, the second one is the gene accuracy. Then they basically try to compare gene plus some of the technique like gene plus ports, gene plus ID, gene plus random fact, and gene plus dropout. And if we see the gene plus dropout accuracy is more better than the others output or others accuracy. And this is the high training accuracy, but also generally all well test safe. So they train all the methods like the 1000 epochs, then evaluate this accuracy on the training set. Then here is the graph classification. They evaluate and compare out the modified gene model and with the original gene model and the other gene method of various expensive label on the real world graph classification dataset. So they use three bioinformatics dataset like MUTAG, PTC, and the proteins, and the two social network like the IMBD and binary and IMBD multi. So if we see the all the comparison with the time complexity, we can see the drop GNN's accuracy is much better than the others experiment, and we also see some of also conflict with sometimes in the real gene and also PGN. But if we think at the overall, we can see the accuracy of drop gene is much better than the others experimental result. And third, if we see the graph properties in regression, so actually they calculate the mean absolute error on DM9 dataset. So DM9 basically the organic molecule dataset, and the best performing model is they actually set up in the bold, and the drop GNN version is improved to corresponding based on the GNN or the mark with the star. So if we see the drop one GNN improves upon the one GNN is most this case, and we see here the MPNN and IGNN is they compare with the drop MPNN and drop one GNN. And if we see the drop MPNN, this is more quite good result than the others approach. So basically, actually they improve this corresponding. So based on the gene, and we see the accuracy of the others comparison baseline result. And so finally, we can say actually they have introduced a theoretical motivator of DropGNN framework, which allows us to easily increase the expressive power of the exciting message passing GNN, both of theory and practice. And if we summarize this, actually they propose a model of agnostic architecture improvement of GNN, and they found in their experiment that the drop GNN work the best on the graph with the smaller degree such as the molecular graph. So basically, they apply a well-known regularization method like dropout in a graph neural network. So that's the simple concept in this research paper. So thank you for concentration and thank you for watching this video.